All right, we are recording now, I hope. Yes, all right. Let's get started in urinary 3. I'm thinking this might be the last urinary system video, and so maybe get through this chapter with 3 videos. Okay, I think I left off on here the last time, urine osmolarity. Remember what osmolarity is? It's the how watery your urine is versus how salty it is. Remember, the more things dissolve in the urine, the saltier it is, the lower the water concentration. The fewer things dissolve in it, the more watery it is, the higher the water concentration. It all depends upon the levels of ADH. That's really the most important hormone when it comes to determining the osmolarity of your urine. So this is all regulation of water, and this will be we'll go over this again in the next chapter on fluids and electrolytes. So how watery your urine is, it's a wide range. Now it's going to be measured in things called milliosmoles, and you don't have to even worry about what a milliosmole is, but low osmolarity means a watery urine. High osmolarity means a very salty urine. So if you're really, really dehydrated, you will be making a very small amount of urine, maybe half a liter per day, and that's the minimum. You have to urinate every day. You have to pee every day. If you're really dehydrated, you'll be making a very small amount of urine, as little as half a liter, and it'll be at what's called 1,200 milliosmoles. That's as salty as you can make your urine. That's your maximum degree of dehydration. So it didn't matter how dehydrated you are. If you're dying of thirst, you still got to make half a liter of urine every day at 1,200 milliosmoles. If you're drinking lots and lots of water, actually maybe drinking too much water, you can make liters and liters of urine, be peeing all day long at a very, very low osmolarity, 50 milliosmoles, if you're overhydrated. So you can either conserve water, be dehydrated, or dump excess water if you're overhydrated. Okay. All depending upon how much ADH there is. Okay. Let's look at these different ion excretions. Starting with potassium. This is on page 980 of the book. And concentrations in filtrate become higher in filtrate due to reabsorption of sodium and water between the cells along the paracellular route. Remember, potassium and sodium go in opposite directions. If you've got a lot of aldosterone, you'll be absorbing lots of sodium. If you're absorbing lots of sodium, you're losing potassium in your urine. If there's not a lot of aldosterone present, then you'll be excreting lots of sodium. You have salty urine, and you'll be reabsorbing potassium. They go in opposite directions. Okay, intercalated ducts continually reabsorb. Principal cells reabsorb depending on the level of aldosterone. And actually, elevated potassium levels are the strongest stimulant for aldosterone secretion. And that's at the bottom of figure 2420, bottom of page 980. I think that's in the next slide. Yeah, right there. 60 to 80% of reabsorption in the PCT. And this is just not regulated absorption. This is automatic reabsorption of potassium. 10 to 20% reabsorption in the nephron loop. That's actually active transport in the ascending loop, nephron loop. then regulate K reabsorption and secretion in collecting ducts. So type A intercalate cells that continuously absorb K. The principal cells vary the K secreted depending upon the aldosterone levels. If there's very little aldosterone, you'll be secreting, you'll be absorbing lots of potassium. You will be losing much. If there's a lot of aldosterone present, you'll be mostly secreting potassium and losing a lot of potassium in your urine. Remember, high potassium in your blood is dangerous. It's neurologically dangerous. You have to regulate how much potassium is in your blood. Okay. Calcium phosphate. These ions are also regulated, and they're regulated by levels of PTH, parathyroid hormone. Regulates how much calcium and phosphate you lose in urine. And these also go in opposite directions. It's like potassium and sodium. If you reabsorb a lot of calcium, you will lose phosphate. If you don't reabsorb calcium, you will reabsorb phosphate. So so like I said, they go in opposite directions also. PTH inhibits phosphate reabsorption in the PCT. Here's something interesting that most of the things in the PCT are automatic. They're not really regulated, they're brought in automatically. But phosphate is regulated in the PCT. So if you have PTH present, you will not reabsorb phosphate, you'll reabsorb calcium if PTH is present. And this is really, this is on the next page, 9A1, figure 2421, shows pH inhibits reabsorption of phosphate in the PCT, PTH stimulates reabsorption of calcium in the DCT. Is that on the next slide? Yeah, that's on the next slide, right here, figure 2421, page 981. Now let's go back to pH here. In pH, what we're concerned about are two other ions. This starts on page 982, bicarbonate ions and hydrogen ions. Now we're looking at different ions for pH. If your blood is too acidic, you'll be secreting hydrogen ions, saving bicarbonate. If your blood is too alkaline, you'll be absorbing hydrogen ions and secreting bicarbonate ions. And more bicarbonate filtered in hydrogen ions, so you must recover these bicarbonate to prevent acidosis. And bicarbonate is not specifically reabsorbed. It's reabsorbed by way of the ubiquitous equation. Water plus CO2 makes carbonic acid. Carbonic acid breaks up into hydrogen ion and bicarbonate. This is why I said before you need to really memorize this equation, because you keep on seeing it over and over again. We'll see it in the next chapter as well. Matter of fact, we'll talk a lot more about pH regulation in the next chapter. Okay. Here is how, this is on page 983, how hydrogen ion is secreted and bicarbonate is reabsorbed. And that's a usual situation because we usually have a little bit more acid in our bodies than base, because acids are made by our metabolism, by lactic acid. And so we always have a little bit of an acid load, and we need to usually secrete hydrogen ion. And this is why urine is almost always acidic. When we do the urinalysis lab, we'll learn that, and so we'll be taking the pH of people's urine, and it's almost always acidic, because we always have this acid load. Apparently, if you're vegan, you often have alkaline urine, but that's sort of unusual. So this is how it's done. As you can see, there's bicarbonate and hydrogen ion in the filtrate. They combine to form carbonic acid, and that breaks up into CO2 and H2O. The CO2 is absorbed, diffuses across the tubular cell in the PCT and nephron loop. That combines with water to form carbonic acid. The bicarbonate ion is reabsorbed into the interstitial fluid across the basolateral border of the cell. And the hydrogen ion is secreted back into the tubular fluid. And that's an automatic process in the PCT. So you're like I was saying, you're not specifically absorbing bicarbonate ion from the tubular fluid. You're absorbing CO2, and that's converted to bicarbonate, and we bring it back to the body and secrete a little bit of hydrogen ion. Later on, into type A intercalated cell, and that's sort of automatic. As I said, automatic in the PCT and the nephron loop, regulated hydrogen ion and H reabsorption secretion in collecting ducts. So the type A intercalated cell will secrete hydrogen ions. The type B will secrete bicarbonate depending upon how acidic and how basic your blood is. It's usually a little acidic, so what happens will mostly be in to the right on page 93, or to the right on this figure, and it's the same thing. CO2 is diffuses into the intercalated cell. It combines with water to form carbonic acid that breaks up into bicarbonate ion, which is reabsorbed into the interstitial fluid, and then hydrogen ion is secreted. And this is how we dump excess hydrogen ion. All right. So as I said, type A intercalated cells secrete hydrogen ion. Type B intercalated cells secrete bicarbonate. And how do they know whether tubular fluid is more acidic or basic? I think it depends on the level of CO2 in the filtrate. So a lot of CO2 is going to come in, and you're going to break up into bicarbonate ion and hydrogen ion and get rid of the excess hydrogen ion. Type B will secrete bicarbonate. It'll be reversed in a type B. You'll bring in CO2, you'll break up into hydrogen ion and bicarbonate. The hydrogen ion will be brought into the interstitial fluid, and the bicarbonate will be secreted back into the tubular lumen. Okay. Substances eliminated as waste. And this is on previous page 982. So urea, uric acid are both reabsorbed and secreted. Creatinine from creatine phosphate is only secreted. Urea half reabsorbed in the PCT, but then secreted in loop of Henle. So all of the urea is still infiltrated in the PCT. So it's kind of odd. It's reabsorbed in the PCT, then secreted in the loop of Henle. So all of the ureas that came into the nephron is still infiltrated the DCT. And then half is reabsorbed in the collecting duct. So you really only clear your body of about half of the urea that comes into the nephron. So the blood leaving the kidneys actually still has close to half of the urea that came into the kidneys. So there's just less urea leaving the kidneys than came into the kidneys. So we don't clear our blood of urea each time it goes through the kidneys. Okay. Drugs and bioactive substances. This is the next page, top of page 984. Certain drugs, antibiotics, morphine, chemotherapy drugs, saccharine chemicals are all drugs that are eliminated in urine. And it is the basis of drug tests. You know, some of these drugs are eliminated in urine as they were when they went into your body. Others are breakdown products. Your liver can break down some of these drugs. You know, the breakdown products are eliminated in urine, but still they're detected in urine. And so that's the basis behind urine drug tests. A little bit of metabolic waste. Urocobilin, a breakdown product of heme groups, and hormone metabolites of hormone breakdown, they're found in urine. And some whole hormones are found in urine. One particularly interesting one is human chorionic gonadotrophin. This is a hormone made by new placentas. And so you mostly find it in pregnant women, and it is the basis behind the urine test for pregnancy. They take this hormone, they inject it into rabbits or horses, and the rabbits and horses make antibodies to it. They take the antibody from that horse or rabbit, they attach a dye molecule to it, and they put it in the paper. And so you pee on the paper, and if it's HCC present, it binds to the antibody, lights up the dye molecule, and you get that blue, I think it's blue cross, which tells you you're pregnant. Because if HCG is in it only comes from a placenta. So if that drug is in your urine, you're pregnant. Okay, peritubular capillaries, these are the capillaries that surround the PCT and the DCT. They have very high caloric osmotic pressure and low hydrostatic pressure. So that means they're almost all reabsorption. Remember, this is the second part of the renal portal system. First set of capillaries are the glomerulus, and they're very high. Remember that, and they're very high in hydrostatic pressure. They're really high hydrostatic pressure, very low osmotic pressure. So they really push things out of the blood. And so when these glomerular capillaries recoalesce into the efferent arteriole, the efferent arteriole is really low pressure. Most of the pressure is bled off into the renal capsule. So it's very low pressure in the peritubular capillaries and relatively high osmotic pressure. So it's almost all reabsorption. It's very similar to the lung capillaries, almost all reabsorption. Tubular secretion, what do we use tubular secretion for? For waste removal and acid-base balance. So that's it. Secretion, remember, is pushing things from the tubular fluid into the blood. Okay, nephron loop. What happens in the nephron loop? And what is the function of the nephron loop? All right. Important thing to note is that sodium, potassium, and chloride are actively transported in the ascending loop. Right. Also, urea is recycled. It's reabsorbed in the collecting duct and then secreted in the loop of Henle. It's recycled. Okay, let's look at the nephron loop first. The second part of this slide, distal convolute tubule and collecting duct. I'm talking too fast. Intercalate cells, acid-base balance. We already talked about that. And the principal cells are where these hormones, aldosterone, ANP, ADH, and PTH works, and we've talked about those already. Here's the establishing the concentration gradient. The nephron loop, or as I learned, the loop of Henle. And this is on the bottom of page 984, and goes on to talk about more that on 95. The nephron loop. Okay, the function of the nephron loop is to establish a concentration gradient in the medulla of the kidney. And when I say concentration gradient, I mean 300 milliosmoles near the top of the medulla, deeper in it. As you go deeper and deeper in the medulla, it gets more and more and more salty, down to 1,200 milliosmoles. And this is how, so notice that the osmolarity of the fluid that's entering the descending loop is 300 milliosmoles. That is the same osmolarity as your blood. And the osmolarity of the fluid in the proximal convolute tubule. Notice as it goes down into the medulla, the descending loop, that tubule is permeable to water, and as it goes deeper and deeper in the medulla, the interstitial fluid in the medulla becomes more and more and more concentrated, saltier and saltier. So, and you can see at the bottom of the nephron loop, there's 1,200 milliosmoles. So water just sucked out of that fluid. So the fluid in the bottom of the nephron loop is 1,200 milliosmoles. And the reason it is because on the ascending loop, as I said, salts are actively transported out of the ascending loop. And the unique thing about the ascending loop is it's completely impermeable to water. It's not permeable to water at all. It's the only part, the only cells in your body that are always 100% impermeable to water. Water does not cross that barrier. Only salts do. Salts are actively transported out of the whole ascending loop. And that's where this concentration gradient comes from. All the salts that are pulled out of the tubular fluid in the ascending loop. So by the time the fluid gets to the top of the ascending loop and becomes actually the distal convolute tubule, it's down to 100 milliosmoles. So it's actually less salty, more watery than the fluid that entered the nephron loop. And that's important. We're going to see later on why that's important. And as it goes through the DCT, it becomes even more water. At the end of the DCT, it's 50 milliosmoles. And this is going to be important for the ability to dump excess water if we need to dump excess water. I'll explain that in a bit. Notice the blood that's the capillary that surrounds the nephron loop is called the vasa recta, and it is also part of the second part of the renal portal system. So the efferent arteriole breaks up into the peritubular capillaries that surround the PCT and DCT. It also breaks up into the vasa recta that surrounds the nephron loop. And it goes in the opposite direction of the fluid that's in the nephron loop. It's called a countercurrent system, so that the blood that comes in to the medulla, water leaves the descending part of the vasa recta, and the blood in the base of the vasa recta is 1,200 milliosmoles. But then it comes back up to the cortex, and salts come out of it, water goes into it, and by the time it gets up near the top of the nephron loop, near the PCT, it's 300 milliosmoles. So it's the same osmolarity that blood should be. Okay. So the collecting duct. Now after DCT, start the collecting duct. So the fluid entering the collecting duct from the DCT is 50 milliosmoles. And the collecting duct wall is differentially permeable to water. That is, if ADH is not present, it is impermeable to water. Water cannot cross it. If ADH is present, it is permeable to water, and water can be reabsorbed. And this allows for control water loss to excrete hypo or hypertonic urine. So hypotonic urine would be urine that's more watery than blood. Hypertonic urine would be urine that's saltier than blood. And so it all depends upon your level of hydration and how much ADH is present. So here's why it's important that the fluid that enters the collecting duct is more watery than the blood. Because if you're really overhydrated, this 50 milliosmol fluid will flow through the collecting duct, and there's no ADH present. So it will flow all the way through the collecting duct into the minor pelvis, and you will excrete lots of watery urine at 50 milliosmoles because you've drank too much water. So that's why it has to be more watery going into the collecting duct. What if it wasn't? What if you were only, if it was 300 milliosmoles at the beginning of the collecting duct? It would flow through the collecting duct, with no ADH present, and then you could only excrete isotonic urine that was the same milliosmoles as your blood. So how could you dump excess water? You wouldn't be able to dump excess water if you didn't get the tubular fluid to be a lower osmolarity than your blood. The opposite problem, say you're really dehydrated. Now you secrete ADH. You make the collecting, the wall of the collecting duct permeable to water. And this fluid, starting off at 50 milliosmoles, flows through an area of 300, 500, 600, 800, 1200 milliosmoles. So water will be sucked through there by osmosis as it goes through the collecting duct, depending upon how dehydrated you are. If you're just medium dehydrated, well, then you maybe only put a little bit of ADH present, and you only bring back part of water in the fluid, and you might excrete urine of 500 or 600 or 800 milliosmoles. But if you're really severely dehydrated, you can do a maximum of 1200 milliosmoles. And that's as hypertonic as you can get your urine, 4 times saltier than blood. That's it. And that's the length of the amount we can conserve water. This is why you can't drink seawater. Seawater has an osmolarity that's higher than 1200 milliosmoles. So when you drink seawater, you bring in so much salt that you have to use water to get rid of that salt. And actually drinking seawater will actually dehydrate you even more, because you can't excrete urine as salty as salt water is. It's more than 1200 milliosmoles. Okay. We mentioned the counter current multiplier keeps high osmolarity in medulla of kidney. This just means the loop of Henle, the reason it exists is to maintain that, to make and maintain that osmolarity gradient in the double. Okay, we talked about the common current exchange and the vasa recta. Okay, urine and renal function tests. We're going to be doing a little bit of this in the lab in the week after next called the urinalysis lab. We'll look at the composition and properties of urine, its appearance, its odor, its specific gravity, which is really a measure of how many things are dissolved. It's very similar to osmolarity. What is its pH? What is its chemical composition? And what kind of cells are suspended in it? Because we'll be spinning it down and looking at the cells. So urine volume. You usually make, usually if you drink the amount of water you should and everything, and you stay relatively hydrated, you usually the average amount of urine produced by a person a day, I think it's 1.5 liters. If you make more than that, it's called polyuria, and you can make many more liters than that. And that's if you're really overhydrated. Then there's oligouria, which is smaller amount of that, like down to 0.5 liter. Anuria is making no urine, and that is really bad, and it can be lethal if it's not taken care of. Because urea at really high concentrations become toxic, and also all of these ions, all the things that are regulated in your blood will go out of whack if your kidneys don't function. All the ions, sodium, potassium, calcium, phosphate, the water concentrations will not, if you're overhydrated or dehydrated, you won't be able to regulate that if you don't make any urine. So urine volume, diabetes, remember there's 2 types of diabetes. Diabetes mellitus, diabetes insipidus. And they're due to the lack of 2 different hormones. Diabetes mellitus, so you should be careful when you say diabetes. Most people think diabetes mellitus when somebody says diabetes. And that is the lack of insulin. And the hallmark of that is having glucose in your urine, because you overwhelm the glucose transport proteins in the PCT if you're untreated diabetes mellitus, because you need insulin to pull glucose into cells, and without that, your blood glucose goes through the roof. It goes through the roof, it ends up in your urine. Remember, your kidneys don't regulate glucose, they conserve it. Sometimes there's a little more glucose in the blood leaving the kidneys than coming in, because remember, the kidneys also do gluconeogenesis. They can make glucose from amino acids. So if you're not eating your proper carbs, there's going to be a little bit more glucose in the blood leaving the kidneys than comes in. But if you're eating your carbs, the same amount of glucose leaves kidneys as comes in. Diabetes insipidus is a lack of ADH. So you make tremendous amounts of really watery urine at 50 milliosmoles because there's no ADH present. So here's the thing. Both untreated conditions makes a huge amount of urine, because if you have a lot of glucose in your urine, the osmolarity is much higher, and you can't suck as much water back in when it goes through the collecting ducts. So you end up making lots of urine. Of course, you make lots of urine in diabetes insipidus because you don't have any ADH present. So back in a day, so just looking at it, so both conditions have the same symptom, large amounts of urine. And back in the day, before dipsticks, in order for physicians to figure out whether it's diabetes mellitus or insipidus, they'd actually taste the urine. Diabetes mellitus has sugar in it, so it tastes sweet. And that's what mellitus means in Latin, actually, sweet. Insipidus is dull tasting, it's tasteless. It's insipid, that's Latin for tasteless. Okay. Fortunately, now we have dipsticks, and physicians don't have to do that anymore. And diuretics, remember, are things that really inhibit ADH. And they used to be used for high blood pressure. People used to give people diuretics to make them pee a lot, so their blood volume goes down and their blood pressure goes down. But now they have much more sophisticated drugs for that. Now, renal function tests, what's called renal clearance. What percent of a particular substance is cleared by your kidneys? And it's figured out by the equation U, which is the urine concentration of this substance, times the volume of urine produced, divided by the plasma concentration of this substance. I'm not going to give you any math problems on the exam dealing with that, but it's important to know what renal clearance is. And it's and starting on evaluating kidney function on page 987, and there's the equation right there, and they call it GFR. Well, for a substance that's not secreted nor reabsorbed, renal clearance is GFR. In fact, that's how they measure GFR. The best way is to inject this stuff called inulin into a vein. And inulin is this carbohydrate that's not reabsorbed, not secreted, and it's completely filterable at the glomerulus. So it ends up in the urine in the same concentration it is in the plasma, and therefore it is a glomerular filtration rate. And glomerular filtration rate, remember, is milliliters per minute. So the clearance of inulin is 125 milligrams per milliliter, and that's GFR. That's how much blood is filtered at the glomerulus. Okay. So, glomerular filtration rate, same as clearance for a substance that's not reabsorbed or secreted. So, here's the thing. If the glomerular filtration, if the clearance of this substance is higher than 125, then it is secreted, right? Because it's higher than it came in the blood. If the amount in the urine is greater than it is in the blood, then it must have been secreted. If, however, the clearance of the substance is below 125, it's below its concentration in the blood, then it was reabsorbed. So, for example, of this, at the bottom of page 97, the real plasma clearance of urea is 70 milliliters per minute. So if it's filtered at a rate of 125 milliliters per minute, then only 70 milliliters per minute is cleared. The rest is reabsorbed. So it's actually about 40% reabsorbed. And a lot of times they just use creatinine because creatinine is secreted a little bit, but not very much. So the clearance of creatinine is pretty close to GFR. The best thing to use is this stuff inulin. Okay, urine storage and elimination. So now we talk a little bit about the anatomy of the plumbing now to get rid of urine. So ureters, remember, are from the kidneys to the bladder. They're they're lined by the same lining as in the bladder. And I forget what that line is called. It'll come to me. The urinary bladder, the smooth muscle that make up the urinary bladder is called the detrusor muscle. We're going to get this transitional epithelium in urine, just like in bladder. And we're going to get those in next week's lab is urinary anatomy. We're going to get that stuff. The urethra is the tube from the bladder to the outside of the body, to the orifice of the urethra. There's two sphincters at the orifice of the urethra. Fortunately, there's one internal sphincter that is opened automatically. It's a parasympathetic reflex that we'll talk about in a moment. And when that opens up, that's when you get the urge, oh, I have to pee. Fortunately, we have an external sphincter that's under voluntary control, and we can keep that closed until we go to the proper time and place to eliminate the urine. An elimination of urine, or peeing, $2 word for peeing is micturition. You won't find too many people going around it and say, pardon me, I have to go micturate right now. And it's a reflex, parasympathetic, to open internal sphincter. And there it is. I forgot about the male. That's right. I forgot. I skipped over that. The male urethra is much longer than the female urethra, and it has three parts: the prostatic urethra, the membranous urethra, and what's called a spongy urethra. So those are going to be right here. Female on the left, obviously, male on the right. So you can see that the male urethra goes to the prostate, goes right to the middle of the prostate gland. Poor engineering there, because older men often have large prostates, and it squeezes at that and makes it hard to urinate. Then there's something called the urogenital diaphragm, where a very short area is called the membranous urethra. And then when the urethra enters the penis, it goes to what's called a spongy urethra, because it goes right through the corpus spongiosum, some of the erectile tissue in the penis. It goes right through the middle of that. And it ends up going through the glans penis, which is the expanded part of this corpus spongiosum at the end of the penis. Because remember, male penis does double duty, right? There's two fluids that goes through the male urethra: urine, which we'll talk about in this chapter, and semen, which we're going to talk about in the last chapter, on the reproductive chapter. And here is the micturition reflex right here. Because I showed you the figures on page 993. Now this is on 995. So here's the urinary bladder. It's got about 100 milliliters in it. When it gets about 300 milliliters in it, the detrusor muscle is stretched. This is detected by stretch receptors, proprioceptors, sends information into the spinal cord to the micturition center, and then this parasympathetic nerves travel down through the spinal cord, out through the pelvic splanchnic nerves, and to the internal sphincter to open up the internal sphincter. And then we have a somatic motor neuron, the prudental nerve, that controls the external sphincter, and we can keep that closed until we, like I said, the right time and place to open up the external sphincter and then be able to urinate. And that's the end of the chapter, and that's the end of urinary 3. Now there's a bunch of slides, kind of odd slides on mushrooms later on in this PowerPoint presentation. And well, I can think of that. And this is a warning about eating the wrong mushrooms. This guy who wrote The Horse Whisperer, he ate the wrong kind of mushrooms. He thought he was eating this kind of mushroom right here called Boletus edulis. It's a choice, really good mushroom, but instead he ate that mushroom, Coronarius speciesissimus, which is also called the angel death mushroom. And he's lucky to be alive. He and his wife lost, and their brother-in-law lost kidney function, had to get kidney transplants. And it was a really stupid mistake. He admits it was a stupid mistake because all he had to do was to turn the mushroom upside down to look at it. This mushroom is a gilled mushroom, has gills. What he thought he was eating, Boletus edulis, has little holes, called boles, has little holes. All he had to do was turn it upside down. But he thought his brother-in-law knew what he was doing, and his brother-in-law thought that he knew what he was doing, and they ate this mushroom, and they lost kidney function and very nearly died. So you got to be really careful. And then these rest of the ones are these mushrooms that I actually collect and eat. They're called inky caps, and they're really easy to identify, and so they're really safe. And they're really identifiable because they do that when they get old, and nothing else does that. So anyway, that's just a real aside. I'm not going to be asking the mushroom questions on the exam. Okay, that's it for urinary 3 and actually the urinary system. So I'll see you later. And if you got any questions on the, remember on these that come up in your readings or watching videos, please let me know. So see you later, and we'll catch you on fluids and electrolytes, the next chapter. Bye-bye for now.